Welcome back. After learning about general state operators in the previous lecture, we now explore the state space of qubits. So let's talk about qubits. So here we have a two-dimensional space, and in the earlier lectures where we talked about the polarization qubit of photons, we met the Pauli operators X and Y and Z, and they had standard 2x2 matrices in which the Z matrix was diagonal, the X matrix was off-diagonal and real, and the Y matrix was off-diagonal and imaginary. And so those are the basic matrices. Now, they are very basic in a very profound sense that we will now explore. So first let me note that if I take the square of any of these matrices, like x squared, well, that's just squaring this matrix, and it gives me the identity matrix. I get the identity, and I also get the identity if I square y, and I get the identity if I square z. And if I take products of two of these matrices, like x and y, then that product will just give me I times z. And now this is true with cyclic permutation, so y times z will give me I times x, as one can easily verify, and z times x gives I times y. And then one can also verify that if I interchange the order of the multiplication, that results in an overall minus sign. So yz product is equal to negative zy product, and zx product is equal to negative xz product. So let's now kind of summarize this by introducing the so-called Pauli vector operator, for which we use the standard symbol sigma, and that's a vector where the x component is made of the x operator, the y component is made of the y operator, and the z component is the z operator. So if we think of this as a three-component vector, then it has this x, y, and z operators as its components. So this is just a vector in the usual vector sense, but it is also an operator because each component of the vector is one of these basic operators. So if we would represent the whole sigma vector as in terms of these matrices, then it would be a column, and each entry in the column is one of these 2x2 matrices. So this is a vector. If I look at a particular component of the vector, say in the direction of some numerical vector A, and this numerical vector A has x component ax, and the y component ay, and the z component az, then the A dot sigma vector, well, it's just what you get from the dot product between these vectors and these vectors. And these are, of course, the Cartesian unit vectors for the coordinate system that we are referring to. And so we get the number ax times the vector x plus the number ay times, we get the number ax times the operator x, the number ay times the operator y, and the number az times the operator z. So this notation is very natural in this context. Now here we have one component of the Pauli vector operator times another component of the Pauli vector operator, and we get a third component of the Pauli vector operator. Here also we have products of a component of the Pauli vector operator, but multiplied by itself. And so if we kind of summarize all of these equations compactly, we have one component of the Pauli vector operator specified by a numerical vector A, and the second component of the Pauli vector operator specified by a second numerical vector B. And then this product, well, if we have the same part of sigma twice, then we just get the identity. So we get the A vector dotted into the B vector. This is just AX times BX plus AY times BY plus AZ times BZ. This is exactly the things that happens, times the identity operator plus, and now here we have the ingredients of the vector product of A and B dot sigma. So let's just check this with a little example. Say we have A equals the unit vector in the x direction and B equals to the unit vector in the y direction. Then the A dot sigma is x, the B dot sigma is y. On the right hand side we have Ex dot Ey, A dot B, that would be 0, and A vector cross B vector, Ex vector cross Ey vector, that's the Ez vector. So we get the Z component of sigma with an I, and that's the Z operator. So we just reproduce this equation. And the other equations are other special cases of this general expression. So we have the Pauli vector operator, and if we take components of it and multiply them, we get a multiple of the identity, or we get another component of the Pauli vector operator, one that is in the direction that is orthogonal to both the direction of A and the direction of B. So the cross product of the two vectors appears here. But this equation tells us that whenever we have a product of two of the Pauli operators x, y, and z, that is equal to a multiple of the identity and another Pauli operator. And then that follows that whatever complicated functions of these Pauli operators we have, in the end, by making use of this relation, we can always write it as a function that is a linear combination of the identity and the Pauli vector operators. So the general operator for the qubit is of the form some multiple of the identity plus a component of the Pauli vector operator. So this is any qubit operator is of this form. What else do we need to know? Well, remembering Born's rule, we need to know about traces. So the first observation is that x and y and z have 0 diagonal sum. So the traces of the Pauli operators are all 0, which also means that the traces of any linear combination of the Pauli operators is equal to 0. So this is true for all numerical vectors A. Well, then what about the product of two of those things? Okay, so the trace of A dot sigma, B dot sigma, well, if that's the trace of A dot B times the identity has trace 2, so we get 2 A dot B plus A cross B times the trace of the sigma vector, but the sigma vector is just made of x, y, and z, so the trace of the sigma vector itself is 0. That's just a statement that we have here. So plus 0. So the trace of A dot sigma, B dot sigma is just 2 times A dot B. Now, if any qubit operator is of this form, then also the statistical operator. So let's just look at what is the trace of such an A. The trace of this A is equal to A0 times the identity. The trace is 2 times A0. And the trace of A dot sigma, well, that is 0 itself. So the trace of A is 2A0. Now, the trace of the statistical operator is 1. So for the statistical operator, this A0 number that appears here will just be a half. So for the statistical operator or the state operator, we have the general form that it is half of the identity, and then something of this kind, for which I will now write S dot sigma. And in this context of the state operator, this S is the Pauli vector, or sometimes called the block vector. We will use these two names interchangeably. Okay, so here is rho equals this. So if rho is of this form, then what does the Born rule say about an expectation value of an operator A? Well, what is the expectation value of A? Well, that would be the trace of A times rho. Okay, so let's work this out. So that's the trace of, and now let's just multiply. That's A0 times 1.5, so we have half A0. Then we have half of A0 times S dot sigma. It's a product here with here. Then we have half of A dot sigma times 1. And then finally, we have half of A dot sigma times S dot sigma, the product of this term with this term. Now, the half A0, well, that's half of the identity. The trace of the identity is 2, so the trace of half A0 is just A0 itself. Then the trace of S dot sigma, the trace of A dot sigma, well, these are traces of this kind, which are both 0. And this is a trace of the kind that we have here. So here we get the trace of A dot sigma, S dot sigma would be 2 times A dot S, but there's a half here. So we just get A dot S. So the trace of A is A0 plus A dot S. For a general operator for a qubit of this form, and the state operator written in this standard form. A particular example is if rho and A is the same. Then we get the trace of rho squared. And here the A0 is a half and the A is half S. So we get a half of 1 plus S dot S. So this is a half plus half of the S vector squared. So the length of the S vector squared. But we know that the trace of rho squared cannot exceed 1. And since this is a two-dimensional system, it has to be larger than a half. It's clearly larger than a half because the S squared is positive, and so we're adding something positive to a half. So clearly this is always larger to a half, and it will only be equal to a half when the S vector is the null vector. So, and then we have the completely mixed state. So let's note this: if S is 0, that happens for the completely mixed state. For a pure state, we get equals 1 here. So for a pure state, S is a unit vector. The length of S equals 1 for a pure state. And for mixed states, we have less than 1 here. So we have the length of S less than 1 for all mixed states. Well, so the allowed vectors here are vectors which at most have length 1, then we have a pure state. If it's a length which is less than 1 but not 0, then we just have some mixed state. If the Pauli vector is the null vector, like the length is 0, then we have the completely mixed state, where rho is just equal to half the identity. Alright, so for a state operator, we have half the identity plus half of the Pauli vector times the Pauli vector operator, or the block vector times the Pauli vector operator, and this numerical vector S that appears here can at most have length 1. If it has length 1, then we are dealing with a pure state. If it is length 0, then we have the completely mixed state. And any qubit operator is such a linear combination of a multiple of the identity and a component of the Pauli vector operator. The expectation value of such an observable with this state operator, the trace of A rho, is just this A0 times this A vector dotted into the Pauli vector. Now, it sort of is implicit here already that if we take the expectation value of A dot sigma with rho, so this is just the expectation value of A dot sigma, well, this is equal to A dot S. But then, since the A is arbitrary, this just says that S itself is equal to the trace of rho times the sigma vector operator. So this is the expectation value of the sigma vector operator. And since this is true for S in general, we can also write the rho as half of 1 plus the expectation value for the sigma vector times the sigma vector. So this is a numerical vector that's just equal to S, and this is the sigma. So this is simply a different way of writing that by identifying the S vector, the Pauli vector, block vector, whatever is your preferred terminology, as the expected value of the Pauli vector operator. So, if we just look at this in general again, then the state space of the qubit is, well, the collection of all those possible state operators, and they are parameterized by this block vector, which is a vector in three-dimensional space, which does not exceed 1 in length. So the collection of all S, the state space is just all S vectors with length not exceeding 1. So this is a ball, the so-called block ball. And the surface of the block ball is the block sphere. That's the surface of the block ball. And so the block ball is all rho represented by S or parameterized by S. The block sphere is all pure states for the qubit. So we have a very simple geometry for the qubit state space. It's just a three-dimensional ball of unit radius, which is this length restriction on the vectors. The pure states that go with the vectors that have unit length, they are sitting on the surface of the ball, the block sphere. The mixed states are inside, and the completely mixed state, which has the block vector of 0 length, that's just at the center of the block ball. In summary, the qubit state space is a unit ball known as the block ball. All the pure states reside on its surface, known as the block sphere. In the next lecture, we study how the qubit state operator is affected by unitary transformations.